Welcome back to Physics 141 Online. I'd like to do an example problem that shows how to calculate the torque produced by a force around a particular point when we're given the force and the location in Cartesian coordinates. And so this is a case where we will generally use unit vectors to calculate the quantity torque, which is, of course, given by the formula tau for torque, and of course torque is a vector, is equal to r cross F. Alright, which if you're not used to dealing with cross products may seem a little bit strange, but I'll show you how to unpack that and apply it in a particular case that's very similar to some of the homework problems that you have. So here is the problem statement. We're given a force that's 2I plus j in units of newtons, and it's applied to some kind of object at a particular point. If you're looking for something tangible to think about, imagine that you've got a sheet of plywood, and there's a certain point, which is at x equals 0, y equals 3, where we drill a hole into the plywood and put a screw into it, and then we're going to tie a rope around that screw and pull on it with a particular force. So this force is applied at that point. And now, rather than just calculate the torque produced by that force around the origin, which is sometimes what we would do, let's pick a different point. We want to know what the torque would be around a different point, which is presumably where the rotation axis for this object would be located. So we'll draw a sketch that will be necessarily kind of a crude sketch, but will give us some idea in the Cartesian coordinate system where these things are applied. And so we've got the standard x and y axes here, and imagine that there's some object that I'm not going to worry about sketching the shape of, but as I said, it could be a sheet of plywood. And there's two important points here. There's the point where the force is applied, which is up here at x equals 0, y equals 3, that's where the force is applied, and then the force itself would be 2 units along I, or the x direction, and then 1 unit along j. So for every 2 units along x, it would go up 1 along y. So that force might look something like this if I sketched it on this coordinate system. Right? So the point up here, of course, is the point that we labeled 0 and 3 for its coordinates, and those are in meters. And now we're calculating the torque around the point 2, 0, which might be right around here on the x-axis. Alright, so that's 2, 0. And what that does for us is it tells us how to draw the r vector, because r always goes from the point where we're calculating the torque, which is usually the rotation axis, to the point where the force is applied. So what I need to do is draw that r vector starting at point 2, 0, going to point 0, 3. So we'll see if I can do this approximately, just to indicate that that is the r vector. And I will the first thing I want to do is write down r using the ij notation. And it's easy to see how you do that, because to go from 2, 0 to 0, 3, you ask yourself, how many units do I have to go along x and how many units along y, right? And so it's got to go 2 units in the negative x direction and then 3 units in the positive y direction. So r, once I realize that, I just can write this down as r equals negative 2I, because remember I is the unit vector along the x direction, plus 3j. And so that, now we already know what f is in Cartesian coordinates, that's given to us. Now we know what r is. And so let's just go ahead and write down then symbolically the torque, which is r cross F. I'm going to put in r as negative 2I, right, plus 3j, and then we form the cross product of that with the f vector, which was 2i plus j. And I'll leave the units out of all of these calculations until the very end, because I know that the r vector, those numbers are in meters, and then the f vector, those numbers are in newtons. So we should get an answer for torque that's in newton meters. Now, how do we evaluate a torque with this kind of expression? Well, cross products, even though they might not be too familiar to you, they obey a distributive law. So that we're going to take this negative 2i and form the cross product with 2i, right? So I'm going to write out 4 terms, and you'll see how this works. Negative 2i cross 2i, and then if I do the same thing with negative 2i and j, this will be minus 2i cross j. And so we're just distributing that negative 2i through the terms of the f vector. So that gives me the first 2 terms. Now I'll do the same thing with the 3j crossed into the 2i and the j. Right? So then this will give us plus 3j cross 2i. And finally, right, 3j cross j plus 3j cross j. And this looks awful, right, because I've got 4 terms, but it turns out that this will simplify. Some of these terms are going to drop out, as we'll see in a minute. So we just have to evaluate each one of these. And one thing I will do, just to make it a little bit easier to work with, the negative 2 and then the 2 here are just magnitudes of the 2 vectors that are forming the cross product. So I can pull them out front. Negative 2 times 2 is negative 4. And so this first term leaves me with negative 4i cross I. You see how that works. The only thing where cross products are different than normal products is that the order is important. For example, when I wrote down 3j cross 2i in the third term, I could not write that 2i cross 3j because that would give me something different. So the order of the cross products is important. Alright, so the first term. Now the second term, negative 2i cross j, I can't really do anything to simplify that. I'll just rewrite it, negative 2 times I cross j. So once I figure out how to evaluate I cross j, then I'll know what the answer is for that one. Now, 3 times 2 is 6, so this is plus 6 j cross I cross I. And then finally the last term is just 3 j cross j. Can't do anything more with that one either. So now, in order to evaluate these unit vector cross products, let me just remind you what unit vectors are. Okay, in a Cartesian coordinate system, the I is the unit vector along the x direction, and so I'll just sketch that in here. J is the unit vector along the y direction, and the z direction has the unit vector k, and that's coming out of the page here. Alright, so I'm going to indicate that by drawing a circle with a dot at the middle, and that represents the tip of an arrow coming out toward us. And so when we use the right-hand rule to evaluate the direction of each of these cross products, we will be referring to this set of unit vectors in the x, y, and z directions. Alright, now in order to evaluate these, remember there's the definition of the cross product. I'm just going to write this down and then we'll refer to it in a minute. A cross B. Okay, what is A cross B? It is a vector where we get the direction from the right-hand rule. And we'll be doing that in just a minute, but we get the magnitude of it by using, so the vertical bars mean magnitude. We take the magnitude of A times the magnitude of B times the sine of the angle between them when we draw them with their tails together. Alright, so if A looks like this and B looks like this, then that angle between them is the angle theta. Alright, so the angle between them is theta. So I've got 4 terms in my torque, so let's just take them one at a time. The first term here is the one that's negative 4 I cross I. So if I can figure out what I cross I is, then I'll know what that first term is. So what's I cross I? Well, I cross I, if you think about it, we're taking the cross product of a vector with itself. And you should look at that and say, well, wait a minute. What's the angle between those two vectors? And the angle between any two vectors that are parallel is 0. Sine of 0 is 0. So this is, if I just write down what the magnitude of that is, a unit vector is a vector with length 1, right? So I has length 1, the other vector has length 1, and then it's the sine of 0. Because they're parallel to each other, like I said. And so that means that any vector crossed into itself is equal to 0. So the first term in my torque expression is 0. The last term will also be 0 because it's j cross j. So number 1, that first term is 0. I'll also then write down over here that the fourth one is going to be 0 because j crossed into itself is equal to 0. And again, what's the reason for that? It's because these vectors are parallel to one another. And that means the angle between them is 0. So I'll just go up to the torque expression and you can see right away the I cross I term and the j cross j term drop out. And if we had a k cross k term, that would be true too. So we're left with just 2 terms in the middle, the second and third term, that we have to evaluate. So we'll look at number 2. What do we do with number 2? Well, there we've got negative 2 times I cross j. So negative 2, right, I cross j, and I cross j we can evaluate. We're going to find out really quickly that the magnitude is just equal to 1. And here, let's do that. That's the term itself is negative 2I cross j. Well, I cross j is a vector that has a magnitude of 1, right? Because it's got magnitude of 1, the I unit vector, and then the j unit vector also has magnitude of 1. The angle between them, think about it for a minute, look over here on the reference coordinate system, I and j are in the x and y directions. The angle between them is 90. So it's 1 times the sine of 90, right? So that's just equal to 1. The magnitude is just equal to 1. Now for the direction. The direction of I cross j. Use the right-hand rule. Right-hand rule, you take the fingers of the right hand, point them along the I direction, and curl them towards the j direction. And if you're using your right hand, you should find that you can only make that motion if your thumb is pointing out of the board, out of the page, along the k direction. Okay, so I'm just going to write that down, that when we use the right hand rule, we find out that I cross j, the vector, is along the k direction according to the right hand rule. Alright, so then what we found is that I cross j has length 1, has magnitude of 1, and it's along the k direction. And so this term here, right, negative 2 I cross j becomes equal to negative 2 times k. We just found that out, right? So that is what the second term gives us. Now the third term is going to be very similar to that. The third term involves j cross I, though. Alright, so 6 j cross I is what we want to evaluate. Now we know already, it's pretty easy to see, that j cross I, just like we did I cross j cross I is going to be a vector that has length equal to 1, Right? The magnitude will be, once again, 1 times 1 times the sine of 90, right? Because the two vectors are 90 degrees apart. That's equal to 1. Now what's the direction? The direction of j cross I. Here, we got to put our fingers along j and curl them towards I. Before, we found that to go from I to j, you do that with your thumb pointing along k, and here it's just the opposite. The only way to curl your fingers of your right hand from the j direction to the I direction is to have your hand oriented so the thumb points into the page. So this j cross I is a vector that's along the negative k direction, negative k hat, or into the page. So 6j cross I gives us 6 times negative k, which is the same thing as negative 6 k hat. And so those second and third terms, we've evaluated them, and so now we can see that the torque that this force produces is equal to negative 2k in Newton meters, right? I'll leave the units out for the moment, minus 6k, and so the answer we get for this torque is negative 8 Newton meters. I'll put the units in now finally, along k hat, or the minus sign of course means that what we really have is a torque of 8 Newton meters along the negative k hat direction. So that's our answer, and this problem is maybe even just a little more complicated than some of the ones on your homework, but it illustrates the basic idea of writing down the r and the f vectors, solving for r if we need to, right? And then forming the cross product using the distributive law. And when you do this, you find out that I cross I and j cross j are equal to 0, so they're gone. Then the two terms in the middle, we evaluated them using the right-hand rule. And anytime you have one unit vector crossed into another one, the magnitude will always be 1, as long as they're 90 degrees apart, like these are. The direction we get through the right-hand rule, and we found out that both of these terms actually ended up in the negative k direction, so they added together. And that's our answer. The units, Newton meters, that's adequate, that's correct for torque. And so the minus k direction just means that when this force is applied to the object at that point, then the torque about the point 20 would be in the negative k direction, which means it would be clockwise. Because if I put my thumb along negative k into the page, the fingers of the right hand would curl clockwise, and that again makes sense just looking at the picture. I hope this is helpful, and I will see you in class.